Professor Osmo Kivinen, researcher. Oh, these are together. Okay. Juha, Hedma, and Dr. Kivinen are from the research unit for the sociology of education, University of Turku, Finland. They have published about the topic of the keynote address, for instance, in Scientometrics, 2013, productivity analysis of research in natural sciences, technology, and clinical medicine, an input-output model applied in comparison of top 300 ranked universities of 4 North European and 4 East Asian countries, and in Scientometrics 2008, Worldwide University Rankings, a Scandinavian approach. They've also had presentations earlier in the IIIS Conference 2011, from rankings to ratings, and input-output analysis of productivity of research and teaching by disciplines, and the other lecture from global performance rankings towards national productivity ratings, productivity of scientific action, technology, and management, social sciences. So,
thank you very much for the introduction, and thank you for the organizers for the opportunity. For the next half hour, I will be talking about a joint research endeavor of Professor Kivinen and myself, and this time it's my turn to do the presentation. And the topic is the productivity of university research in 6 main fields in selected US states and EU countries. So in this presentation, we will demonstrate some ways in which productivity analysis of research by fields will provide an appropriate evidence base for science policy that intends to follow the rationale of performance-based funding. It's not saying that we're promoting the idea of performance-based funding. We're just saying that what the analysis tells from the perspective of performance-based funding. So on the bottom, you find a simplified core idea of what is understood about performance-based funding. The idea is usually that well-performing units would receive more resources than less successful ones because the well-performing units are thus provided with an opportunity to strengthen their competitive edge in the international competition, of course, whereas less-performing institutions are provided with incentives to perform better. That's the basic idea of performance-based funding. But in the last instance, a sophisticated national research policy relies on constantly improving analysis on productivity of research groups, departments, institutions by different fields. And always the evaluation should be done in each field's own terms. And that's what we're kind of demonstrating here with the 6 different fields, that we cannot compare when we talk about productivity, we cannot do comparisons across the fields. And the key measure of productivity, I know that's why I just put it here, the key measure of productivity is the ratio of output to input. The input side should not be forgotten. And then again, I would say that it's very, very hard to have any meaningful discussion about productivity without explicating the relationship between output and input. So that is the measure that we just cannot avoid. Some kind of relation between output and input. And due to worldwide tendency to increasingly orientate science policy, this is going on in every country around the world, to orientate the science policy towards performance and competition mechanisms, even such universities which have already established an excellent level of research, the most famous ones, even those. They have to keep on running as fast as they can in order to keep in the same place. Jamil Salmi applies here the metaphor of a Red Queen effect from Alice in Wonderland. So that's why the whole presentation is kind of in 2 parts. All that's said in this slide can be put in the form that making the world top is one thing. And that's the broader analysis that we start from. But then staying there is another. And then we focus on those that are already there and what they are doing today and forgetting about the history, what's going on today. But the first part is a lot about also including history. Or I would say historical data. So let us start first to find out the world top 300 in different fields. And here's the set of indicators that we start with. And you can find more details from the National Taiwan University's webpage, for example. But just to give you a broad overview, that now we're just measuring the publication and citation volumes of different research units. And 40% comes from the present output, which is publication-based indicators. There they are Web of Science articles in the last 11 years, Web of Science articles in the current year. But now 60% comes from impact of past output. And past output means that publications during the last 11 years. And how much they have then collected citations. That's where we start from. And by applying the above criteria, we find that from 2018 to 2014, out of some 16,000 universities in the world, that's the IAU figure, 16,000. We can go to 17,000, but 16,000 is a amount of universities in the world. No more than 688 from 42 countries have made the world top 300 research at least in 1 out of 6 main fields. And now you can see the 6 main fields under there. It's life sciences, natural sciences, social sciences, agriculture, clinical medicine, and technology. And in all those 300, based on that criteria, is evaluated for 7 years. And that's about 5% of universities in the world make, at least in one of these fields, they have so-called top research going on. And when we talk about countries, it's about 15% of all countries in the world. And to say something about the fields, of course, these can be broken down to hundreds of subfields. But that's not the topic today. We can, open up every field into details. But we keep this broad level now. So the first thing is to look at how does research of universities residing in USA, EU, and China compare with each other in terms of world top 300 in 6 main fields. So where does the top research reside in the world globally? And here are the first results. The share of world top 300 placements in 6 main fields, and now we only here draw USA, EU, and China, and as you know, there's a lot of other countries in the world. And giving you an example, if we take social sciences, there's 48% of the top research is residing in USA, 30% in EU, so that leaves about 22% for the rest of the world. And in all other 5 fields, as you see, EU leads slightly in life sciences, a little more in agriculture, and I'm saying that in relation to US. A little more in technology than medicine and natural science. EU has the largest lead. And as you can see, technology in China is the highest percentage in China, 11%, but it's still a lot behind US and EU. So here is the last figure. The result is that EU and US still enjoy a wide margin against their main challenger, China, in all 6 fields. And US leads in social sciences, EU leads in other 5. But if we apply the principle of relative advantage here, known in economics, that principle suggests that US is at its strongest in social sciences, life sciences, and agriculture. An economist would say that US should, could, and would specialize in those fields. And then EU is then strongest in natural science, clinical medicine, and technology. And I will return to, now we go to the more focused analysis with the 4 US states and 4 EU countries. And I will return to these relative advantage questions in the end. So I hope you remember how it goes now. But in the last slide, we'll come back to that. So now we want to ask the question that how to stay in the top 300. And we take a more focused look at 4 US states and 4 EU countries, all qualifying as rich in terms of knowledge capital and economic prospects. That is the OECD launched term. And I'm not saying that even OECD says that these are the 4 best in those terms. No, but they are above the best. Okay. But the 4 states that we have now taken here is the Massachusetts, or selected, is Massachusetts, Connecticut, New Jersey, Minnesota. And the 4 EU countries is Belgium, Finland, Germany, and Netherlands. And here's just first drawing, and do not yet care about the field so much, but here's just drawing the world top 300 placements in 6 main fields in these countries. And as you can see, Germany leads by a wide margin to the second one, Netherlands, almost twice as many. Top 300 placements. So size does matter even in top research, but not only size, which we will see in the next slide actually. But as you can see, the smallest ones are now for Minnesota, Connecticut, New Jersey, Finland, Belgium, and so forth.
I have a question. In order to understand what you are presenting, California, you just didn't look at it, or California didn't make the cut?
Sorry?
California.
California. Oh, it's not included here.
Okay.
I can show it then if, yeah. The reason was the knowledge capital of OECD, and knowledge capital means basically the cognitive skills of mathematics and science of secondary school students. And that's where these states score high. And I'm not even promoting that idea, but I'm using it as a tool. And I will test this in the end. You will see the results. So, yes, that was when we don't consider the input side at all. And now we use just money as input, okay? The size of the economy, the GDP. Let's just relate the top research to the size of the economy. The value 1 now tells that the volume of top research corresponds to the volume of the economy. So as you can see, Massachusetts has 1.75 times larger share of world's top research than its share of world's GDP. And then second comes Finland, Belgium, Netherlands, Connecticut, Germany, New Jersey, and Minnesota. And I open up that figure a little bit. This is just looking at the US states with the same figure, again, share of top research in relation to share of GDP. Okay, price, money, whatever. But this is interesting because you see that in every field, Massachusetts is number 1, Connecticut number 2, Minnesota number 3, New Jersey number 3, and Minnesota number 4. When we go to Europe, you don't find that. The top placements change by the fields. And the whole order changes by the fields. So it's not like everything is done in the same place. And then when we put it together, we see that that's how it looks. Massachusetts and surprisingly Finland changes the top position. Or leads the pack in different fields. So let's go towards a more up-to-date evidence base encompassing human input of top research. We have only talked about money. Now let's start talking about the human input of top research. Because money does not produce the top research. It's important, money is important, it's essential, but it does not produce the top research. So we have to take a more focused look here and take into account the human input put into the top research. And again, we use this 4-state, 4-country as a case demonstration. This could be done, California could be here, but this is a demonstration. And the up-to-date here means that now you'll see it here. The first thing to do, what I mean by up-to-date, let's forget about the citations altogether. We don't need those. Let's forget about the articles in the last 11 years. Let's just focus on up-to-date indicators. The Web of Science articles in the current year. And then the other one is the articles in the current year in high-impact journals. 2 indicators, 50-50. So this is saying that how the machine is producing today. And then integrating an indicator of human input, which is here the research man-years employed in that top research. And the source is from the US side is the National Science Foundation, National Center for Education Statistics, and from the European side is the European University of Data Collection. And we only need now two measures, two relatively reduced measures. The WOS productivity, Web of Science productivity, relates the Web of Science articles to research years. And the other measure, high impact productivity, relates articles in the high impact journals to research years. And based on those two very reduced measures, we apply this 4-step rating, where A++ is the highest rating. That means that in both indicators, you're doing more than your input share would make us expect, let's say that way. And we will now focus on how these countries and universities reach this A++ rating, which now we'll say that it's a productive unit doing top research. And here's first natural science, and this is how it looks like. It's a little bit different what we saw earlier. Now we see that the US states have the A++ ratings except Connecticut. And this is just now focusing on the articles and human input. Netherlands is also in the A++ rating. Clinical medicine, which was in the area of EU countries, Connecticut, Massachusetts, Minnesota, New Jersey is a little bit with the Belgium, Finland, and Germany. And Finland and Germany, well, I will not talk about language issues here. We know that English is the lingua franca of science, but we will talk about that tomorrow more. And here's technology. Massachusetts, New Jersey, Minnesota, and Netherlands get the A++ rating. And then social sciences, Massachusetts, Connecticut, and New Jersey, and again Netherlands from the European side. Minnesota is productive in the high impact articles per research years, but not on the Web of Science per research year. And the middle is the whole world. The origo is the whole world, the productivity in that field in the whole world. So I could basically put all the countries here, but now we are focusing on only these 8. And here's life sciences against Massachusetts, Connecticut, Netherlands, New Jersey. Minnesota and Belgium are very close to the origo. And here's then agriculture against Massachusetts, Minnesota, New Jersey. Now Belgium and Netherlands are both also in the A++. So then going even deeper, going university by university, and now just looking at the A++, those that are doing world top research and doing it productively. And this, of course, is very strict. We could take the A+ also, but this is the A++ rating and the world top 300 research by fields and universities. And you will find that, to take some examples, that in Massachusetts, not surprisingly probably, but Harvard, MIT get the A++ rating in all 6 fields. Tufts in 5. And then Princeton from New Jersey gets also 5. Minnesota 4. And in Connecticut, you have the University of Connecticut Health Center and Yale getting 3. The same in Europe. A lot of Dutch universities getting A++ ratings, as you can see. And Utrecht, 6. And Groningen, University of Groningen, also 6. And in Belgium, it's the Catholic Universities of Leuven and Louvain. Both get 6. Germany, the social science, there's no social science, but the best is Technical University of Munich with 5. And Finland, Helsinki has 3. So summarizing that table, we see that the most productive top research units are found in Netherlands, altogether 49. And yet the whole amount of units reaching the top 300 in their field in Netherlands is 60. So we get a ratio of 0.82 of those being A++ productive. And then Massachusetts and Germany has both 27. And Finland is now left there with Minnesota with 4. Now Finland has 17 top 300 units though, but only 4 with A++ productivity. And that gives us a ratio of 0.24. Now, we can think that policy-wise what to do in Finland. I talk about now in Finland. Some would say that, well, let's try to reduce those that make the top 300, because there's very little you can do with the 4 that already are productive. They are productive even without the policy. But what I would suggest that this tells us that, for example, in Germany, there's a huge capacity having those 171. So with a certain policy, it would be probably a bit better goal to think that how to even improve those, their productivity. And then looking at Netherlands, you could say that, well, almost their whole capacity is already in use. That's a good thing. There's not much need for a policy there. And it's actually true. Well, sorry, I went the other way. I promised to test if we have the right 4 states and 4 countries. Here's the test. We ran the same analysis to all 50 US states and all 28 EU countries. And there you can find that only in natural sciences in US, these 4 countries do not give you the best. They do not represent the most productive natural scientific top research in US. So we should probably in natural science take other 4 than these. And in EU, in science and technology, we should not use these 4. They do not make the let's say, the more productive half of the countries. So, this is the last question. How does EU and US compare in current productivity of top research? So now I'm talking about current, today. And this is how they compare. So that's why now the order is very different from where we started. When EU led in 5 fields and US in 1, now US leads in every field. And the good question is what to make of it now. We have 2 kinds of results here. And the answer is articulated here. We had 2 questions. The first one was how to make the world top in research, and the other one was how to stay there while you're there. So in terms of making world top in research, the principle of relative advantage suggests that US is at its strongest in social sciences, life sciences, and agriculture. EU, in turn, is at its strongest in natural science, clinical medicine, and technology. This is where we started from. But in terms of staying in the world top, US seems to have a challenge, particularly in agriculture and life science. That's what we could predict from this more up-to-date evidence. And then EU in turn seems to have a challenge, particularly in natural science and technology. That's where they now have the most challenge in staying in world top. They have reached it already, but staying there. And here's some samples if we want to read more, what they were already mentioned there. So we already have English language publications also. We have the obligation to publish a lot in Finnish, so, but we have English also. And I want to thank you for your attention.